I am pleased to introduce Professor Nathalie Tufenkji from McGill University. Nathalie is she was recently promoted to full professor in the chemical engineering department at McGill. She received her undergraduate degree from McGill University in chemical engineering in 1999. And she then went to Yale University, where she got a PhD in environmental engineering, working with Meni Elimelech, where she did some really important work on filtration. And for her PhD work, she received the AWWA Best PhD Thesis Award. After her PhD, she moved back to McGill, where she currently holds a Canada Research Chair in Biocolloids and Surfaces, and leads a research group focusing on nanomaterial biological membrane interactions, with applications to the protection of water resources, engineering of biosensors, antimicrobial materials, and the development of safe nanomaterials and nanotechnology. So with that, we're very happy to have you visit Minnesota, Nathalie.
Thank you. Thank you. Thanks, Thank you very much. Thank you, Santiago, for this kind introduction and for the invitation to be here today. This is actually my first time in Minnesota. It's wonderful to be here. It was great to meet with your students and several faculty members, and also to have this opportunity to talk to you about some of the work we're doing at McGill in the area of environmental nanotechnology using QCM-D. So the incorporation of nanomaterials into consumer products is growing at a very fast rate. As you can see in this figure, the world market incorporating nanotechnology into consumer products is expected to reach $3 trillion by 2020. Along with this increased rapid growth in the incorporation of nanomaterials comes growing concerns with the potential environmental and health risks of nano in our everyday lives. This. So this figure here shows you some of the sources of nanomaterials to the environment. For example, accidental release in manufacturing sites may lead to introduction of nanomaterials into our environment. As well, recent studies show that nanomaterials are ending up in biosolids in wastewater treatment facilities that are then applied to agricultural land. And so there's growing concerns about the potential transfer of these toxic nanomaterials into food supplies. And of course, in some cases, we're actually intentionally introducing nanomaterials into the environment. For example, in situ remediation, where we inject reactive, for example, zero-valent iron nanoparticles into the subsurface for remediation of contaminated sites. So there's growing sources of introduction of nanomaterials into the environment. And one of the questions that we're interested in looking at in our laboratory at McGill is the environmental fate of these materials and also the impacts of these materials. Now, specifically, we focus on aquatic subsurface environments, and we're interested in environmental transformations, aggregation of these materials, and their mobility in these environments, so their transport and deposition behavior. Now, typically, or traditionally, when we study the behavior of these materials in these kinds of environments, what we do is we'll use lab-scale column studies, where we pack columns with granular aquifer material, and we can do these studies under very well-controlled conditions to understand the transport and deposition behavior of those materials. Well, we can also zoom in to this aquifer material, and we can consider what's going on at the grain scale. What are the processes that control the deposition behavior of these particles on the grain surface, the release of these materials and these transformations, really at the micro scale? So we consider again here our aquifer grain, and we consider the region where the fluid is flowing parallel to the grain surface. And this is where the QCM-D, or quartz crystal microbalance with dissipation monitoring, becomes relevant. So the QCM-D is basically a nanobalance. It's a sensor that's mounted inside a flow module where the flow is parallel to the sensor surface. And it's basically a nanobalance that allows you to weigh at the level of nanograms per square centimeter. So in this case here, we can see the nanomaterials are flowing parallel to the sensor surface. And as the particles deposit on the sensor surface, you're basically detecting this change in mass at the surface. Now, one of the advantages with using QCM-D is we can readily modify this crystal surface with different thin films. For example, alumina, iron oxides, sort of to mimic patches that we might find on sediment grains. We can also coat the surface with, for example, dissolved organic materials. We can absorb biomacromolecules. So we can really test how different environmental conditions influence the behavior of nanomaterials interacting with these model sediment grains. So the quartz sensor is basically a quartz crystal. And when we apply a voltage across this crystal, it starts to oscillate at a resonance frequency. Now, as mass deposits on the surface of this crystal, the frequency of oscillation will actually decrease. So it's actually this change, this shift in the frequency of oscillation that we're detecting. And this shift in the frequency of oscillation can be related to the change in mass. And this is done using the classical Sauerbrey model. So you can see here, this is some representative data where I'm showing the frequency shift, so this change in the frequency of oscillation. First we have our baseline. We're just injecting electrolyte into the flow module. So we've baselined the system, and then we start injecting our nanomaterials. And we could see a decrease, so a negative frequency shift with time. So as these nanoparticles deposit on the surface, you have a decrease in the oscillation frequency. Now, if we look at the slope of this curve here, we basically have the change in frequency with time. But if we apply this Sauerbrey model, where the change in frequency is proportional to the mass deposited, then we effectively have the change in mass with time, which is our particle deposition rate. So in my slides, I'll show you, when I talk about this value R of D, R subscript D, it's the particle deposition rate onto the sensor surface. Okay, so you notice here we have QCM-D, so we have this dissipation term. In QCM-D, we're also measuring the dissipation in the system. So imagine again our sensor surface, it's oscillating, but now imagine we turn off the voltage. You're going to have energy losses in the system, so this energy is going to dissipate. Now the way this energy dissipates is a function of the stiffness of the film on the surface. So if you have a rigid film like a brick, you're going to have very low or little dissipation. But if you can imagine a viscoelastic film like Jell-O, now you're going to have more energy losses as when you turn off this power to the crystal. So you have more dissipation or a higher delta D. So in QCM-D, we're actually measuring these two parameters simultaneously. You're measuring the frequency shifts as mass deposits on the surface, and also these dissipation shifts, approximately a few hundred times per second. It's turning off, turning on the power to the crystal. So this is an example representative data. You can see these are the dissipation shifts. So first we baseline with electrolyte. When we deposit these nanomaterials on the surface, we see this increase in dissipation, so energy loss in the system. So the delta D gives us the viscoelasticity or the rheology of the film that's deposited, and the delta F gives us some idea of the mass that's deposited. And we get these measurements simultaneously in real time. Okay, so let's take a look at some real data. In this first study that I'm showing you, we were working with 4 different nanomaterials. 2 model polystyrene latex particles that we chose, approximately 20 nanometers in size. The first one is carboxylated, and the second particle is sulfate modified. We also worked with 2 quantum dots, and these are fluorescent nanoparticles. And the first quantum dot has a polyethylene glycol coating, and the second quantum dot has a polyacrylic acid coating. We're suspending these particles in potassium chloride, just a very clean system, and we're depositing them on an aluminum oxide coated quartz sensor. So at the pH that we're doing these experiments, at pH 5, the alumina surface is positively charged, and our particles are negatively charged. So we have what we refer to as a favorable condition for deposition. Those particles want to deposit. So let's look at some data here. What I'm showing you here is the normalized particle deposition rate on the quartz sensor, on the alumina-coated surface, as a function of the ionic strength at which we conducted these experiments. So I'm showing you this, I mentioned this is a normalized deposition rate. We normalize the deposition rate by the mass transport limited rate. We can calculate the mass transport limited rate using the Szmalkowski-Levitch approximation that I'm showing you here. So it's basically just an analytical solution to convective diffusion equation. And what we're doing is, given the concentration that we inject and the particle size and the fluid properties and the module geometry, we can predict the rate of deposition of those particles on the surface. So what we've done is we've normalized the measured rate by this theoretical mass transport limited rate. So first we look at the data for the polystyrene latex particles. What you see is the deposition rate, the normalized rate is around 1. So those particles are freely depositing on the surface. They're happily depositing. You can see that at the highest ionic strength, there's a little more variation. And this is because at that high ionic strength, the particles start to aggregate. So it's a little bit more difficult to calculate the theoretical mass transport limited rate for normalization. I'll draw your attention to these blue symbols here. Now here I've plotted the data for the pegylated quantum dots. And you can see that as we increase the ionic strength, the deposition rate decreases. And this is in qualitative agreement with the LVO theory of colloidal stability for a negatively charged particle depositing on a positively charged surface. So we weren't too surprised to see these results. We also saw that the deposition rate for these quantum dots about at least an order of magnitude lower than what we saw for the polystyrene latex particles. And this is because these PEG molecules on the surface of the quantum dot create this electrosteric stabilization, preventing the particles from readily depositing on the surface. Now, the behavior of this PAA-coated quantum dot was quite different. When we looked at the behavior of these particles, we see now that the deposition rate increases with increasing ionic strength. And this behavior can be attributed to the special nature of the polyacrylic acid molecules coating this quantum dot. Now, at low ionic strengths, these PAA molecules adopt a extended conformation due to intramolecular and intermolecular forces. So when this particle tries to deposit on the alumina surface, it's experiencing some electrosteric stabilization. But when you increase the ionic strength, these PAA molecules collapse, and now the particle more readily deposits on the surface. And you can see the deposition rate approaches the mass transport limited rate at that higher ionic strength. But again, we did see that at the low ionic strengths, the deposition rate was quite lower than what we expected based on the mass transport limited rate. So we can gain some insights into particle deposition kinetics using this technique. Get some insights into how the different coatings influence particle deposition behavior. But I showed you earlier, I mentioned this dissipation, and we can measure these dissipations simultaneously. So here in this figure, I'm showing you the frequency shifts as particles deposit on the surface, as well as these dissipation shifts that are measured simultaneously. Now, if we look at the ratio of delta D to delta F, this gives us some insight into the stiffness of the film that's deposited on the surface, where a value of 10 to the minus 7 is an empirical limit for a transition from a stiff to a viscoelastic regime. So let's take a look at these ratios for the data that I showed you previously. Those experiments that I showed you, we're depositing again where we had deposited these 4 different particles on the alumina surface. So now, instead of showing you just the deposition rates, I'm showing you these delta D by delta F ratios. And again, this is at the different ionic strengths that we conducted these experiments. So if we look at the data for the polystyrene latex particles, we see that all of the delta D by delta F ratios fall in the stiff regime. So these particles are forming relatively stiff films on the surface. But the results are quite different and more interesting when we look at the polymer-coated quantum dots. So here you see with the pegylated quantum dot, we see that these delta D by delta F ratios fall in the viscoelastic regime. So this pegylated quantum dot is forming these more viscoelastic or jello-ish-like films on the surface. But again, this PAA-coated quantum dot yielded some really interesting results. You see at the lowest ionic strength, it seems to form a viscoelastic film. But when we increased the ionic strength to about 10 millimolar, we saw that the films became more stiff. So what's happening here is those polyelectrolytes, they're collapsing. So now the particle can deposit and form a more rigid film, more stiff bond with the surface. But what happens when we increase the ionic strength even further is you can see the films become more viscoelastic again. So what's happening here, as we increase the ionic strength further, the particles start to aggregate. So now you have these aggregates depositing on the surface, and you can see that aggregates, because they're so clumpy, are being felt as a more viscoelastic layer or a more viscoelastic film. Remember, this crystal is oscillating, so when these big clumps deposit, they're giving rise to more energy loss as that crystal oscillates. And we see that also with the pegylated quantum dot. You can see at this high ionic strengths, where the quantum dots start to aggregate, we see a rise in the viscoelasticity of the films. So aggregated systems can tend to give us a little bit of trouble in QCM-D. We have to make sure that we're very careful about how we interpret these measurements. Now, I mentioned to you at the very beginning, when particles deposit on the QCM sensor, we expect to see a decrease in the frequency of oscillation, right? We expect to see this negative frequency shift. And when we have a negative frequency shift, that directly can be translated to a mass on the surface. And this is based on the Sauerbrei model, right? However, sometimes, unfortunately, challengingly for us, we actually detect positive frequency shifts. And this is kind of theoretically unusual for us because a positive frequency shift actually theoretically means we have loss of mass from the surface. So when we do these experiments and we know we're depositing particles on the surface, we're introducing particles, and we see positive frequency shifts, we start scratching our heads. So here's one example from a few years back where we deposited titanium dioxide nanoparticles onto a silica-coated sensor. So this one is different. It's a negatively charged surface, and we have our negatively charged particles. They're suspended in 100 millimolar sodium nitrate at pH 9. So they're quite negatively charged under these conditions. And what you see here in gray, the dissipation measurements, those delta D values, and in black, the frequency shifts. You see positive frequency shifts. So when my postdoc first did this experiment and brought me the data, I thought he made a mistake in the way he prepared his sample or the way he ran the experiments. I said, go back and please repeat this experiment. And he went back and he repeated it. And he came back to me and I said, wow, you really don't know what you're doing, you know. I really said. And then he kept repeating the experiment and he kept getting the same results. So I said, okay, there might be something here. So we decided, let's do the experiment over a wider range of conditions. Let's figure out what's going on here. We did the experiment over different pHs, different ionic strengths, and we started collecting a larger set of data. And we sat down and we looked at this data. We realized when we have conditions where strong repulsive electrostatic interactions dominate, so where we would expect to have weak attachment of the particles, this is where we see positive frequency shifts. So repulsive conditions, like here, where we have pH 9, these particles are very negatively charged, and the silica surface is very negatively charged. They just don't want to stick, but still we're trying to sense the sticking, and we're sensing something happening here. Something is happening. So we're sensing these positive frequency shifts. So we came to the realization that this behavior can actually be very well modeled by what's called a coupled resonance theory. So what is this coupled resonance theory? So again, take our QCM crystal. Our QCM crystal can be described as a resonator, having a mass m and a spring constant k. And in classical QCM studies, classically QCM was developed to study absorption of small molecules such as proteins. And in these classical studies where small molecules like proteins deposit on the QCM crystal, these small molecules actually deposit or bind quite rigidly to the QCM crystal. So you can imagine this, you have this crystal, you have these small molecules binding quite rigidly. You can see how the mass, the combined mass, is the mass of the crystal now plus really the mass of that protein, which is really bound rigidly. So the combined system gives you this negative frequency shift as we would expect. And it's very well described or in accordance with the Sauerbrei model, right? Now imagine what's happening when you have this large particle depositing on your sensor surface. You have this large particle, and it's in contact by this single contact point. So now, when this crystal is oscillating, this particle just cannot follow the crystal. It's not the same kind of attachment or adsorption, if you will, as the molecular adsorption we saw here. This particle actually acts as a second resonator with its own spring constant and resonance frequency. And this is what we mean by coupled resonance. So when the crystal oscillates at a very low frequency, and we have our particle, and the crystal oscillates at a low frequency, the particle can actually follow the movement of the crystal. And when it does that, the particle is sensed as an added mass. As long as it can follow the movement of the crystal, it's sensed as added mass. But if now we make our crystal oscillate at a very high frequency, the particle cannot follow the movement of the crystal any longer. Sorry, I can't do that. I'm not very coordinated. Excuse me. So now at these high oscillation frequencies, when the particle cannot follow, it's actually creating these counteracting forces. Okay? And now the sensor is actually feeling these counteracting forces. And the counteracting forces that it feels are actually going to be a function of the stiffness of this bond. Okay? So now the sensor is not really feeling the mass anymore. What it's actually feeling is the stiffness of this bond. Okay? And that's what we mean by coupled resonance, and this is why it leads to positive frequency shifts, or why we observe these positive frequency shifts. So we wanted to understand this coupled resonance behavior a little better. So we designed this experiment where we were working with these silica nanocrystals, or new next generation kind of quantum dots. And these silica nanocrystals were coated with different organic acids. In this case, I'm showing you some data with a silica nanocrystal coated with undecanoic acid. And these particles, I shouldn't say the students suspended them in a calcium chloride solution at different ionic strengths. And we're depositing them on a silica-coated crystal at pH 5. So the particles are negatively charged. The sensor surface is negatively charged. We want to promote this coupled resonance behavior. Okay, so in this figure here, what I'm showing you are these frequency shifts that we measured when we deposited these particles on the sensor surface at different overtone numbers. So this overtone number, I didn't mention it earlier, but what it is, it's the different resonance frequencies that you can measure in the QCM. You can measure low overtone numbers or low sensor frequencies, and you can move up overtones. You can sense up to high overtone numbers or high frequencies. Okay? So what I'm showing you is just the data for one experiment. This is, or a number of experiments, but the same condition, the average values. This is all the same experiment, but at different overtones. Okay? And what we're seeing is that over the range of overtones, the frequency shift is pretty much stable. It's about -10, -11 hertz. Okay? So we are detecting a negative frequency shift. This is in accordance with the Saubre model, what we would expect if the particles are depositing on the surface. And what tells us that it's Saubre behavior is that the frequency shifts are stable over the order of the overtones. So in other words, the crystal is oscillating slowly. Sorry, that's slow. Then the particle is following. But even when the crystal is oscillating fast, the particle is following, because the same frequency shift is being detected. Okay? But what happens now if I suspend these particles in a higher ionic strength solution? Theoretically, I would expect to see more deposition of my particles. And if I would expect to see more deposition of the particles, I expect to see an even more negative frequency shift. But when we did these experiments, we saw that the frequency shift actually became more positive. So opposite direction to what we were expecting. We can see here that at the low overtones, the frequency shifts are either just slightly negative or near zero. And then at the higher overtones, they actually become more positive. So what's happening here is at this high ionic strength of 3 millimolar, the particles start forming aggregates, large aggregates. So now you have these aggregates depositing on the surface. And these aggregates, as the crystal is trying to oscillate, the aggregates can't keep up. You could think of them as getting stuck in the stagnant fluid that's sitting above the crystal. Okay? And this is why the sensor is not sensing these particles as added mass anymore. It's these counteracting forces that the sensor is sensing. At the low oscillation frequencies, when the sensor is not moving very rapidly, at these lower overtones, the sensor is probably feeling the mass a little bit. And this is why the values are a little bit negative at the low overtones. But when the crystal starts oscillating very fast, now the particle or the aggregates really cannot be sensed anymore. And this is why the frequency shift keeps going up at those higher oscillation or overtones. So we have to be very careful about using QCM-D in determining nanoparticle deposition behavior when we have aggregates forming. We did these experiments with different silica nanocrystals under different conditions, and what we observed is that we have this transition from Sauer-Brey-like behavior to non-Sauer-Brey or coupled resonance behavior when we have a critical aggregate size of about 700 nanometers. So below a certain aggregate size, we seem to see this Sauer-Brey-like behavior. Particles deposit, and the crystal can sense this as a mass because the particles are small enough that they're depositing rigidly and can be sensed as added mass. But when that aggregate size gets too big or reaches a critical size, now the sensor simply cannot sense it as added mass, but rather it's creating these counteracting forces and loss in energy. Okay. In this second part of my presentation, I'm going to shift gears a little bit and tell you about some work that we've been doing using supported lipid bilayers as model membranes. Now, QCM has been used by other researchers to study the formation of supported lipid bilayers as model cell membranes. And more recently, QCM has been used to study the interaction of nanoparticles or other dissolved toxins, for example, with lipid bilayers. So we were really interested to see how we can work with this technique to study the interaction of our nanomaterials with supported lipid bilayers as model cell membranes. And the idea here is to understand the potential cytotoxicity of nanomaterials to model cell membranes, or to develop nanomaterials for drug delivery, for example, where you need to understand how the nanomaterials interact with model cell membranes. Okay, so to form these lipid bilayers, we start with lipid vesicles. So we have our lipid vesicles and we deposit them on our sensor surface. And when we reach a certain surface coverage of these vesicles, they actually spontaneously collapse and form these planar arrangements of phospholipids. Now, these lipid bilayers are actually thin films on the order of about 4 to 5 nanometers in thickness. And others have shown that the properties of these underlying substrate can actually influence the mechanical and rheological properties of the bilayer that sits above the substrate. So this raised some concerns, because if the underlying substrate is actually influencing the properties of the bilayer, but we want to understand the bilayer, and real cell membranes don't have this supporting underlying substrate, they're actually free-floating membranes. So this raises some concerns for us about the actual relevance of using supported lipid bilayers to study different phenomena relevant to cell membranes. So we decided to look at this question, whether the interaction between our underlying substrate and the supported bilayer has an effect on how this bilayer or membrane responds to our nanoparticles that we might want to be studying interacting with this bilayer. Now, this is not, one of the challenges in studying this question is that the typical techniques used to characterize thin films, such as ellipsometry and spectroscopy and atomic force microscopy, they're not best suited to study this thin interfacial region between the bilayer and the underlying substrate. So we hypothesized that QCM-D could be a useful technique to study this interfacial region between our bilayer and the underlying substrate. And also to understand how the nanoparticles, as they deposit on the bilayer, might influence the bilayer properties and how that whole interaction plays out together. Okay, so first I'll show you how we're forming these bilayers. So we're working with mixtures of lipids. We have two lipids here. They're mixed in a ratio of 2:1. The POPE is an overall net charge neutral lipid, and the POPG is a net negatively charged lipid. So when we mix these in a ratio of 2:1, we have a net negative charged membrane. So we mix them together, we make these vesicles, and we then deposit these vesicles here. We're depositing the vesicles on an alumina-coated crystal. Okay? And all this is done in the QCM flow module. So you have your alumina-coated crystal. I'm showing you in green the frequency shift as we deposit these vesicles. You can see nice negative frequency shift. We're detecting the mass that's depositing. And at a certain surface coverage, these vesicles collapse. And you can see there's a slight increase in the frequency shift. This is because of the water that's released from inside the vesicles. So it's a little bit of a loss of mass from the surface. You see a little bit of a rise in the frequency shift, and then the frequency shift stabilizes. The dissipation shift is shown in red. And you can see very small dissipation shifts, 0.1. So this tells us that the bilayer is very well coupled to the substrate. Very little energy losses, if you will, as that crystal is oscillating, right? And we have very stable bilayers. When we repeat the formation, we always get the same frequency and dissipation shifts. So once we have the bilayer, really the question that we wanted to answer was, can we tune this interaction between the bilayer and the underlying substrate? In other words, can we make the bilayer more firmly attached or less firmly attached? Can we tune that interaction? So to do this, we proposed that we can do this by modulating the pH inside our system. Because we know that alumina, if we increase the pH, you can see the zeta potential here, this is literature data, the zeta potential will decrease. So if we can modulate the pH from 7, 7.58 to 8.5, as this alumina substrate becomes less positively charged, we would expect to have less electrostatic attraction, because our bilayer, just to remind you, is net negatively charged. So we have less electrostatic attraction. So would this work? Will this allow us, would this technique allow us to study how this interaction between our bilayer and our substrate plays a role? So I'll show you the work that we did to tune this interaction. And once we establish that, I'll show you how some work we did to look at how the different nanoparticles interact with our bilayer, and what can QCM tell us about this interaction. And finally, I want to see if I tune this interaction between the bilayer and the underlying substrate. For example, if I make the bilayer less firmly attached to the substrate, does that influence how the nanoparticles interact with my bilayer? Okay, so in this experiment here, what we did is we formed the bilayer on the alumina substrate. So we have our bilayer formed. And then I start modulating the pH inside the flow module. I always say I, sorry, not me. The student was doing the experiment. So we're modulating the pH here. Okay, so what I'm showing you is the dissipation shift. Okay, so we start at pH 7, and we increase to pH 7.5. We don't see any change. But when we went up to pH 8 and then 8.5, see, these are very small dissipation shifts. It's a very sensitive technique. But we're able to detect these very small changes in the dissipation. So what is happening here? There's more dissipation, more energy loss in the system. What's actually effectively happening is as we increase the pH, and the alumina substrate is now less positively charged, the bilayer is just a little more weakly attracted to the substrate, so it's like slipping a little bit on the surface. So you're basically detecting that little bit of slipping of the bilayer. Okay? Now what we found exciting was when we decreased the pH back to 7. When we decrease the pH back to 7, we see that the dissipation is recovered. Okay, we got back to the original dissipation. We were all excited because this tells us two things. It tells us that the interaction between the bilayer and the substrate is actually electrostatically controlled. But it also tells us that we didn't disrupt our bilayer. Because if we disrupted the bilayer, we probably would not recover this original dissipation value. So now we have a technique that allows us to tailor the interaction between our bilayer and the underlying substrate simply by modulating the pH. And we have another technique, just by returning the pH back to the original value, we have a method to indirectly detect the bilayer integrity. Okay? So in other words, if this dissipation value did not fully recover, if it was not fully reversible, then we know that we have some bilayer disruption. So we're glad to see that just by modulating the pH between 7 and 8.5, we're not disrupting the bilayer. So here there's no nanoparticles. It's really just the bare bilayer. But of course, we want to introduce nanomaterials. So many researchers have worked with nanomaterials and studied how they interact with bilayers. And mostly what you'll see is that when particles are oppositely charged to the bilayer, they tend to be disruptive. But when they're like charged to the bilayer, they tend to be generally benign. So here we just selected two very model polystyrene latex particles, the carboxylated particle, which is negatively charged, and the amidine functionalized particle, which is positively charged. And both particles are 20 nanometers in diameter. And we're doing these experiments at pH 7. Okay? And remember, just to remind you, at pH 7 is where we had the most electrostatic attraction. So that's why we chose this condition, just to have the bilayer is well coupled to the substrate. So here I'm showing you the results of the experiments where we deposited the carboxylated nanoparticles onto the bilayer. So what I'm showing you, I'm not showing you the bilayer formation. That was done previously. We formed the bilayer, and then we'd start depositing the carboxylated nanoparticles onto the bilayer. So you can see this nice negative frequency shift. There's actually, even though they're negatively charged, and the bilayer has a net negative charge, they're still depositing on the bilayer. And during this duration, we're injecting nanoparticles. Okay? But it's stabilized here. Not much more particles seem to be depositing, but still we're injecting. And at this time point here, we stopped the injection of the nanoparticles. Okay? We stopped the injection, and now what we want to do is we want to see what's going on with our bilayer. Is it disrupted? Is it happy? So this is where we do our pH modulation. Okay? So there's no nanoparticles being injected during this pH modulation. We're just changing the pH of the solution inside the module. So this is what I'm showing you here, is these dissipation shifts during this pH modulation. So we baseline here to 0, and you can see when you increase the pH, there's an increase in this dissipation shift. So there's more dissipation of energy in the system as you increase the pH. So that, remember, that bilayer is kind of slipping on the substrate. But I want to draw your attention to the fact that these dissipation values are slightly larger than what we saw for the bare bilayer. And this is because the nanoparticles that are now sitting on top of my bilayer are giving rise to more energy loss. Okay? They're giving rise to more energy dissipation. I also want to draw your attention to this dissipation value here when we returned the pH back to 7. Remember with the bare bilayer, when we returned the pH back to 7, we recovered the original dissipation value. But now here, when we return the pH to 7, it almost recovers. These are, this is a fairly small scale here, 0.8. So we almost fully recovered the original dissipation value, but there's a little bit of a discrepancy. So there's some slight bilayer damage. Okay, so that was with the carboxylated nanoparticles, but we really wanted to see what would happen if we threw positively charged nanoparticles at this bilayer. So now we have a fresh bilayer, and we're introducing these positively charged amidine latex particles. Now we see that the result is really dramatically different. So the first thing you see is you have this really rapid deposition of these particles on the bilayer, and look at the order of this frequency shift, 150 hertz almost. So there's a huge frequency shift. These particles just want to deposit onto the oppositely charged bilayer. And then we saw that it reached this first plateau. And we thought, oh, okay, we're done. There's nothing else really to look at. Fine, you're depositing. But then my student said, no, I'm going to keep injecting particles. So all here, he's injecting particles. Then he started seeing this second deposition phase, or what seems to be a deposition phase. So we start seeing this huge drop, about 400 hertz. Something really dramatic is happening here to our bilayer. So this huge drop, and then a second plateau is reached. And again, right, so he starts scratching your head. He says, okay, repeat this experiment. And he keeps repeating it, and he keeps seeing the same behavior. So we wanted to understand what's happening here, so we decided, okay, let's do this experiment, but we're going to stop the experiment at specific interesting time points. Okay, and I pointed those out with these little colored boxes. We're going to stop the experiment at these time points, and when we stop it, we're going to modulate the pH of the system. Because that pH modulation, right, tells about the bilayer integrity. Okay, so he would do this experiment, and then he stopped it at time point 1, 2, and 3. Let's look at these time points 1, 2, and 3. So I'm showing you the dissipation shifts when we did this pH modulation. Okay, so you can see time point 1 right here in the beginning of this first deposition phase. When we change the pH, there's a little bit of a shift in dissipation. And then at the last, when we return the pH to 7, we recover the original dissipation value. So there's no real bilayer disruption at point 1. At point 2, again, we have this dissipation goes up a little bit with the increasing pH, and then we recover back the original dissipation. So again, there's not much disruption. Point 3, we start seeing some drift. We didn't quite recover that original dissipation. So point 3, you can see here is the first plateau. I mean, we've had a lot of nanoparticles depositing on this bilayer by the time you reach point 3. So we'd expect to see something happening here. We took the crystal out of the sensor module, and we looked at it by fluorescence microscopy. Here I should mention the bilayers were spiked with fluorescent lipids so that we can see them by fluorescence microscopy. And when you don't have any particles, you see the whole image is fluorescent green. But here where you see almost no fluorescence, you see some like faded fluorescence, it's because it's coated in particles. I don't know how well you can see that, but it's covered in particles. So this is at time point 3. You see there's like a monolayer of coverage of the bilayer by nanoparticles. And when we translate these frequency shifts into mass, it actually directly translates to approximately full surface coverage that we would expect. Okay, so fine, we can see how it looks at time point 3, but we want to see what's happening at these later time points. So when we did these pH modulation experiments, we started seeing some pretty dramatic responses. Time point 4, right here at the beginning of the second phase, you see much larger dissipation shifts, and you can see we're really far off from where we started when we returned to pH 7. pH 5 is point 5, is very erratic behavior. And at point 6, we have complete breakdown. As we increase the pH, there's just no predictable response. And when we return the pH to 7, this dissipation is not going anywhere back to its original value. So we think what's happening here, well, at point 6, you have complete bilayer disruption. Okay? So what this pH modulation tells us that we do at each time point is that we have a clear transition from a very pH responsive bilayer at the first plateau to a completely unresponsive, damaged bilayer at the second plateau. And we looked at time point 6. This was a really interesting time point for us, and we took the crystals out of the sensor module again, and we looked at them by fluorescence microscopy. And here you can see evidence of hole formation in the bilayer. Depending on where you look, you see coalescence of holes, complete disruption of the bilayer, and here as well, again, some complete disruption of the bilayer. So this figure here shows you that data that I just showed you in the previous slide, but I also plotted the dissipation shifts. And I wanted to show you this because you see how large these dissipation shifts are as these particles are introduced into the system. What we think is happening here is at the first plateau, you've reached this monolayer, if you will, for full surface coverage. But when you keep introducing, because we're always introducing particles here, what happens is lipids start being lifted out of the bilayer, and now you start forming these aggregates of nanoparticles and lipids, and it's these aggregates that are sitting, and you saw it in those fluorescent microscope images, there's all kinds of clumps kind of being created. And what happens is these big clumps are what are giving rise to these large dissipation shifts, or these large energy losses in the system. So these experiments that I showed you here were all done where the particles were deposited on the bilayer at pH 7. So remember I mentioned to you I chose that condition because my bilayer is well coupled to the substrate. But I want to see what happens when the bilayer is not well coupled to the substrate. What would happen? What would happen if I introduce nanoparticles and now my bilayer is not well coupled to the substrate? So to do this, I can just run the experiment, but at different pHs. Remember, if I increase the pH, now my bilayer kind of lifts off. Okay, we have to be very careful what we say, but lifts off the substrate. And now what happens if I introduce these disruptive particles? Okay. So Nareman repeated these experiments, but first we wanted to make sure that when we change the pH, we're not modifying the properties of the particles. So we measured the hydrodynamic diameter and the zeta potential, and we could see that there's no significant change when we modulate this pH. So we're sure that the particles themselves are kind of the same at these different pHs. And now we deposit them on our bilayer at our different pHs. The green curve is the curve you saw earlier at pH 7. And now he repeated the experiments at 7.5, 8, and 8.5. And the clear trend that we see here is that as we increase the pH, you can see that the curves are shifting here towards the left, right? So what's happening, what you see is that this transition between this first plateau and the second phase is happening much earlier. So in other words, at pH 8.5, or at the higher pHs, where the bilayer is now less coupled to the substrate, it's actually more susceptible to damage. It's being disrupted faster. Okay? So when there's a weaker interaction between our bilayer and our underlying substrate, that bilayer is more delicate, if you will. It's more susceptible to damage. And we see this because this transition happens much earlier or much faster. So the interaction between the bilayer and the underlying substrate clearly plays a role in the response of the membrane or the bilayer to something that may damage it, such as a nanoparticle or another material that we might be interested in studying. So this is important for us because it tells us that we have to be very careful on how we design our experiments to study, where we're working with supported lipid bilayers, to study the potential disruptive effects of different materials. Because we'll get draw far different conclusions depending on whether the bilayer is very well coupled to the surface or less well coupled to that substrate. Okay, so just to recap kind of some of the main points I was talking about, I showed you how QCM-D can be a useful tool to study particle deposition kinetics and particle deposition behavior and how different particle properties influence particle deposition behavior. I showed you how QCM-D can also be an interesting technique to probe the stiffness of films that are depositing on a surface. I also mentioned how we have to be very careful whether we're operating in the Saubre regime or the coupled resonance regime. And finally, we saw how QCM-D can also be a complementary tool for nanotoxicity studies, as well as the development of safe nanomaterials. I want to highlight the work of, obviously, the students who did this work. Ivan was a PhD student in my group who did most of the nanoparticle deposition studies that I showed you in the first part of my talk. He's now a professor in Mexico, actually at Iberoamericana, I was telling you about. Nareman did his master's with me, and he did all that lipid bilayer work. That was his master's project. Adam is our QCM-D expert. He was a postdoc in my group, and Andreas is also a postdoc in my group working on the lipid bilayer work. So thank you very much for your kindness, and I'd be glad to answer any questions that you might have.
Questions for Nathalie?
I wondered if you'd been able to work with any toxicologists and kind of couple what you're being able to measure at a very precise and detailed scale with what people are seeing with real cells, and if you can then use that as a way to move your work forward in terms of modeling and predictability?
Thanks, Paige. That's a great question. So actually, we just started working with Kristen Shermer at ETH, where she's doing the work with the whole cells, the whole organism, and we're doing the work with the lipid bilayers. But I should admit that we've only been working with lipid bilayers for 2 years. So we're still in the beginning of learning how to work with them, and we really do hope to expand what we're doing and to extend to whole cells and whole organisms and have that direct, that really nice flow of at different length scales. Yeah.
In terms of the QCM studies on these lipid bilayers and the implications for understanding the effects of nanoparticles on lipid bilayers, what are the implications of what you showed us? Is it better then to do the experiments at, say, pH 7 where they're tightly bound, or at pH 8.5 where they're not so tightly bound? It would seem to me to be the latter, if you're trying to compare to what's happening with cells where the cells aren't bound to a solid surface.
Yeah, I think you raise a good question. If you're interested in designing a safe nanomaterial, and you do an experiment at, say, at pH 7, and you don't, you stop the experiment here and say, hey, this is not disruptive at all. This is great. This is a safe nanomaterial. Whereas if you did that same experiment at pH 8.5, where the membrane is more susceptible to damage, then you'll get a very different, you'll draw a different conclusion. And also, I think it's important to come back to the idea that in real cell membranes, the cell membrane is free floating, doesn't have this substrate. So the closer we can get to that, I think the better off we are. In that sense, I think it makes more sense to work with these higher pHs where the membrane is more free floating.
Well, I have a very naive question about your interpretation of the loss of actually breakage of your bilayer. If you say that if it's stronger bond, and I believe in the previous slide you showed that pieces of bilayer were just pulled out.
Oh yes, okay, I think I know which one.
Yeah.
This one?
Yes, yes. But on the other hand, if your bond is not as strong, what are the forces which destroy your bilayer? So like, you need stronger forces to pull the parts out.
So I'm not sure I understand
Well,
the question.
because my understanding, if you have less interaction between your particles and your bilayer, that means your forces, according to this visual interpretation, are lower. So in this case, for me, it's just not clear what really damages your bilayer in this case.
Okay, so the particle itself is positively charged, and the lipids are net negatively charged. There's always going to be this electrostatic attraction between the particles and the lipids. What we're referring to by when we change the pH, it's the underlying substrate, that is becoming, less positively charged. Yeah, exactly.
What do you think is occurring in the bilayer at low levels of deposition, where it seems like the frequency and the dissipation is changing a little bit, but it's still able to be recovered?
Okay, so do you mean, I think you mean here?
Yeah,
Okay.
like 0.2.
What I think is happening is just the particles, they're oppositely charged to the bilayer, they're happily depositing. But I guess it's too early for them to really start seeing disruption. Okay, maybe there's not enough coverage at that point, at point 2, to get disruption. But when we keep introducing particles, I mean, they're probably coming in and hitting some of the particles that are already depositing and starting to cause, kind of like a pulling of the particles from the bilayer. And this is where it's kind of starts a snowball effect. And I think that's what's happening here is a snowball or avalanche effect that we're seeing. Does that answer your question?
I think so.
Because we know when we look at the microscope images, at least, it doesn't seem to be any strong evidence of much disruption at these earlier time points. So I really think this is kind of like this initiation of this avalanche that's happening right here as we just keep introducing particles.
What sort of coverage are you expecting to see in the environment on the cells?
That's a good question. I guess here this was really more of a proof of concept experiment, kind of pummeled the membrane with lots of particles to see if we can actually test this technique. I think in the real environment you would see much lower exposures than what we're exposing our membranes to here. And one of the things we wanted to see here is how we can use QCM-D to better understand mechanisms of disruption. And for example, and also when we do the imaging, we can see hole formation. This gives us some insights into potential applications in drug delivery, for example.
I wondered, because you have this figure there, and I'm wondering about size, and related to what we were talking about when we were chatting earlier, are these nanoparticles, or are some nanoparticles that are used frequently small enough to get into the cell bilayer and into, I mean, you can imagine that if it's at about the same size as that hydrophilic head group, that it seems like it could disrupt it much more completely and much more quickly, especially if you then start to get aggregation of those nanoparticles. And so I just was wondering about the sizes. Are the sizes really giant compared to the cell membrane, or are they similar in size?
Okay, that's a great question because I forgot to mention, disclaimer, this is not drawn to scale. The particles are actually much larger than what's shown here. I'm sorry I didn't mention that. Yeah, I mean, like I mentioned, this is about 4 to 5 nanometers wide, and these particles are, the particles we worked with are 20 nanometers in size, right? So this is really not drawn to scale, it's really just to get a conceptual idea. But yeah, some studies have shown that particles can penetrate and start filling in the leaflets in between these two leaflets here. But those were particles on the order of like 8 nanometers in size. We haven't gone down that small yet. There's still a lot of work we want to do. But definitely some studies have shown that particles can penetrate the membrane and sit in between those leaflets. There's a lot of different routes of disruption or mechanisms of disruption.
Thank you.
Did that answer your question?
Yeah, perfect, thank you.
So if I understood correctly, what you're measuring is a hydrated mass, right?
Exactly.
So you're considering the hydration water in everything you've told us
Exactly,
here.
exactly.
Okay.
And I didn't mention it here, but we also do ellipsometry, which gives us the dry mass.
Okay.
So we can also understand, we can kind of subtract out the water by doing combined. We have a module that allows us to do combined ellipsometry with QCM-D.
Oh, nice.
So.
Any other questions for Nathalie?
Well, I guess if these particles are introduced in the environment and then, for example, the positively charged particles, and then you're ingested, I would imagine, like say via water, that they're going to be negatively charged anyway.
Yeah, exactly.
So
They're gonna get
should
coated
you
with-
study positively charged particles at all, or not?
Yeah, that's a great question. So for us, this was really like, just a scientific question. We wanted to see kind of if our technique would work to understand, this pH modulation technique would help us to understand bilayer disruption. But I agree with you, especially these particles, especially in biological fluids, they're going to be coated with what we call a protein corona. So that's the next step. Nariman, who did this work, is staying on to do his PhD, and that's one of the things that he wants to work on is studying different protein coronas that might be present in biological fluids, how they influence the interaction of nanoparticles with lipid bilayers. And this is really the most simplistic model you can work with. We really have to expand to start introducing things like cholesterol into these lipid membranes, bilayer proteins. There's a lot more. This is really the most simplistic approach you can take. And really, we just did it as a proof of concept. Start dabbling in lipid bilayers.
So if you were to immobilize a monolayer of cells on your sensor and do this study, would you think that that system is far too complex for QCM-D on account of these wobbly, potentially this monolayer of cells would be viscoelastic, and it would be like trying to do, it would add too much noise potentially to the system, no? Do you have any?
Yeah, it's not easy to work with things like whole cells, like bacteria, for example, right? We recently published a paper where we worked with biofilms. I have to say it very carefully because we worked with biofilms, but really what we said in the paper is we're not studying the biofilm. So if you imagine a biofilm like this large forming on the substrate, we're really studying the interface between the substrate and that biofilm, because that's really what it's an interfacial technique. And the penetration depth is on the order of about 100 to 120 nanometers. You're not going very far out into the fluid. So if, in the case of a bacterium, which is 1 micron, this big on this QCM substrate, you have to be very careful about what kind of conclusions you draw from those experiments. To be very aware of the limitations of the technique.
Any other questions for Nathalie? Well, let's thank the speaker again.
Thank you so much.
And join us for the reception.